Okay, so now we got inequalities between two triangles. This is the way, rather than just algebraically tying together inequalities, we can actually compare angles and sides in one triangle with angles and sides in another. And it's based on one simple idea, the hinge in a door. Okay, so the big picture is the hinge theorem, otherwise known as the side angle side inequality. But the idea is, if we have two sides and we lock those two sides so they're always the same, right? This is set, okay? And then we just open up the angle. Well, that means these 2 points are literally moving away from each other. And so that side gets longer. That's it. So if we have two sides set and we open the angle between them so the angle gets bigger, then the third side is enlarged. We also have the converse of that. That's going to be the SSS inequality. And that's if we have two sides that are set and we enlarge the side here, then the consequence is it enlarges the angle. Okay? That's the idea. And that's how we can compare two triangles. So here's the first theorem. Okay, the SAS inequality or the hinge theorem says, so if we have these two triangles and we know that these two sides match these two sides, and then if we know that this is an angle that's bigger than this small one, well then that means we took, in this right triangle, we opened the angle wider, so that must mean this side, where the angle got opened bigger, is a bigger side than this small, right? That's the idea. Or maybe I could write the like given kind of thing in blue, and then the consequence in pink. So if that's helpful. So the blue is what was given to you, and then the pink is the, well, oh, it became bigger. Oh, not G got changed into pink. But that's the idea. Okay, so let's use it in a proof here. Here, we say, okay, we're given all this information. It's shown. We got the YZ and the XZ. We got the Z is the midpoint here. Okay, so let's use that first. We go, okay, well, we're given Z is midpoint of AC. Well, how can we use that, right? Well, the only way you could start anything with using the very thing that was given as a word, right? The only way we could do that is if we actually say the definition of a word, right? Otherwise, what are we going to do with a word, right? So the definition of the midpoint is that, and you could either say lengths are equal or segments are congruent. I'm going to use the segments are congruent because we're going to try and set up this hinge theorem inequality, okay? So I'm going to start by saying AZ is congruent to ZC. All right, now let's look at what we have in this triangle. Okay, so we have this is congruent to this, and we have this here and this here. Okay, so we've got the two congruent sides in these two triangles. Then let's look at what else we're given. So I'm just going to state that too. We're given the YZ, and we're given that's congruent to XZ. Okay, I wrote it backwards just because of space, but we're given that. Okay, so we have the two sides, and then we're even given the angle here. So the angle is the measure of angle CZY is greater than the measure of angle I'm going out of the box here, AZX. All right, so that's the very setup for the hinge theorem or the SAS, right? So we're given two sides, and then it says this is a big angle, and this is a small angle. Okay, well then you put those together. So this was, sorry, I forgot to write some things here. So this was the definition of midpoint. I get so caught up in the proof and thinking about the next step, forgot the reasons. This was also given. So those together are the SAS inequality or the hinge theorem. You could call it either one. I like side angle side just because that's what you have here is you have a side angle side, but it's an inequality because the angles aren't equal. So I think side angle side, triangle inequality. I think that's a good name for it. All right, so now what we're stating is if we have a bigger angle, two same sides opening to a bigger angle, then the consequence is this side is bigger than this side. So the consequence is CY is greater than AX, okay? Now, that's not what it was saying, because right, that would just be literally like state the theorem. So what they're saying is go a little further. They also give us that these are congruent, and they want us to prove that this whole side is bigger than this whole side. Okay, I see what you mean. Okay, let's start over here. What we're going to do is just add the same value to both sides. So let's start. They give us that by is the same as bx, right? Well, if those are congruent, that was given, well, then that means, woof, that was a rough writing given, okay? And then we got by equals bx. That's the very definition, right? So now we're in the world of algebra. That's the definition of congruent segments. Okay, so now we're in the world of algebra. Now look at what we can do. Since by and bx are the same, we could right here add them together and say, well, cy, which one do I want to add to cy? I want to add by on that side. So what I could do is I could start with the cy is greater than ax. And then what I could do is add to it. I could say, well, I could add on one side the by and on the other side the bx, right? And that's just the additive property of inequality. That's just saying if you have one side is greater than the other and you add the same value to both sides. Oh, and I wrote by. You could do by to both sides, but we could do, it doesn't have to be the same lettering, it just has to be the same numerical value. And since by and bx are the same, we could add that on both sides. Now we just got barely anything left to finish this proof. All we need to do is show that those two segments add up to be, I'm going to shrink this a tiny bit for space. All we have to do is show that those two add up. I mean, look at on the left. AX and BX, that's, whoops, I wasn't drawing. AX and BX is the whole segment. And BY and CY is the whole segment. So let's just write that. Right? So the segment addition part just says, well, CY plus BY equals, what's CB? Yeah, CB. Or let's do BC so it'll match the lettering at the beginning. It doesn't matter, right? So here's the segment addition postulate. And now we could sub that in for the left. And I'm going to do it on the right also. I'm going to say, well, also, over here we have AX plus BX. Right? And just look at the picture. AX plus BX, segment addition postulate, is equal to AB. So we're going to sub all three of these things in here. And on the left, what do we have now? BC. And that's bigger than on the right. What do we have? AB. That's exactly what they wanted us to prove. And so here, this was just the substitution property of inequality. Okay, and on the right here, I forgot to write segment addition postulate. Okay, so that's one example of a proof using the Hinge theorem combined with other stuff. Okay, now let's do one in reverse. So the converse of that is saying, what if we start with, and again, I'll do it in blue. So we start with these two sides are congruent to these two sides. And then what they tell us is, if this is a big side and this is a small side. So now we have two sides that are the same, but they open up to a third side that's smaller or bigger. Well, then the consequence of that is the very converse of the last one, which just says that angle 1 is the big angle and angle 2 is the small angle. Right? That's it. Right? That's the consequence. So now let's try and use that. So we're going to try and find three sides, two of which are the same, and then the third side of those two triangles are going to be different with an inequality, and we're going to use that. And here they give us that inequality, okay? All right, so how are we going to use that? Well, let's look. We want to get AOB and BOC. So AOB, so this angle, we want to get that this is big, compared to BOC, that this is small. BOC is small. Okay, these are the two angles we want to compare. So those are probably the very two triangles. So let's look at what we're given. All right, and I'll mark it on the picture. AB is the same as CD. Okay, so these two are the same. And then, let's see, what are we given down here? AB is parallel. So this is parallel to the bottom. Okay. And now we want to get that CD is bigger than, oh, sorry, and we're given that CD is bigger than AD. So this is big. No, this is small. And this is big. All right. Oh, so it looks like maybe what we'll have to do here is actually deal with these two triangles and then use their vertical angles since we're given those sides right there. So actually we want to kind of prove this. So let's jump into it. Well, the hard sticking point here is if we want to compare these two triangles, then either way, whether we're jumping for this triangle and this one or the top two, we need to find two congruent sides that are the same. Now they share a side by reflexive, and so if I want to deal with like angle to side, then the other side I need to show for the SAS or the SSS inequality is I need to show that these two sides are congruent, AO and OC. Well, how could I do that? Now, this is going to be a really common type of proof that you guys are going to do. This is actually a parallelogram, and so we get two pairs of congruent triangles. This pair and this pair are congruent, or that's a pair. And then these two triangles are congruent. They're flipped around because of alternate interior angles. So like the top angle on the right is the bottom angle on the left. So let's go ahead and prove that the top triangle and the bottom triangle are congruent. Okay, so what do we have in the top triangle? Well, we have angle A. Let's do alternate interior angles. So let's do angle OAC is congruent to angle OCD. Okay, that's alternate interior angle theorem. And then we also have the other pair of alternate interior angles. So that was along this transversal. And then along this transversal end parallel lines, we have these two angles are congruent. So let's establish that. That's angle OBC is congruent to angle ODC. That's also the alt-int angle theorem. Okay, I'm going to zoom in here so I can shrink this. I'm writing gigantic when it's zoomed out. Okay, so we have those two. And then we also have a side is congruent. We have AB is congruent to CD. We always need at least one side length is the same. Okay, that was given. So when we combine these, right, so this angle and this angle match this angle and this angle. So then triangle ABO, now careful the order here because it's flipped around, is congruent to A to B to O. It's from 1 to 2 to so C to D to O. Okay, that was by ASA triangle congruence. Now that those are congruent, we can get these sides. So CO and AO match. Okay, so CO is congruent to AO. That's what we wanted. Okay, and then we can establish that the side in between OD is congruent to itself. So this is CPCTC. Then we could also say that side OD is congruent to itself. Right? That's the reflexive property of equality. And now we can use the theorem. Reflexive prop of congruence, I almost said equality. So now we can use the theorem, right? So we now have, I'm going to clean up some of this picture here. I'm going to leave what we want, those angles big and small here. Okay, I'm going to leave those. But look at what we have. We just proved that this side is congruent to this side and reflexive, these two sides. So now we have three sides, two are equal and one's big. With three sides, two are equal and one that's small. So that's the very SSS inequality, right? So I'll write the other given now that we're moving on to really use the theorem. So the other given was that CD was bigger than AD. So now we have a relationship with all three sides, okay? Two that are the same and one that's bigger. That by the SSS inequality, or the converse of the Hinge theorem, however you word it, is going to say that the big angle, so angle COD, measure of angle COD, is bigger than the measure of angle AOD. There we go. So SSS triangle inequality. Another way is you could call it the converse of the Hinge theorem if you really like the name Hinge theorem. Okay, so now that we've got that established, we've used the actual inequality. So now I'm going to erase all this. So now what we've got is, this is big and this is small, but what do we know? We know vertical angles, so let's just go ahead and do vertical angles. Okay, so I'm going to I'll zoom out now just so I can see the picture. So AOD and BOC are the same. So angle AOD is the same as angle BOC. That's by the very vertical angle theorem. And then really, if we're going to use substitution, I should say that their measures are the same. So that way we can really use algebra and substitution. And so now if I establish that by the very definition of congruent angles, and then I do the same thing on the other side, right? So on the left, it's COD and what they want in the end, COD and AOB. So AOB and COD. AOB and COD, the measure of those two are the same. Oh, I started with the measure of them are the same. That's the definition of congruent angles, but that only comes after vertical angles. Let's slide that down a little bit. And so we got angle AOB is congruent to angle COD, and that was by the vertical angle theorem. So vertical angle theorem. Okay. So all we're doing is really substituting out values. We know that this is bigger, so we just substitute an equal value. And we know this is smaller, so we just substitute a smaller value. And so now going back down to the proof, we could just do some substitution here and bringing it all together. We get on the left, instead of a COD, we put in an equivalent measure of angle AOB. And that's greater than, and on the right, instead of AOD, we just substitute in measure of angle BOC. So that was a hard one, right? That was like, you had to prove a triangle congruence. That was just substitution. So this was a much harder one. No promises that it wouldn't be on a test, but this was definitely a more challenging proof. Okay, now let's more literally just use the theorems algebraically, because that's what's going to happen a lot of times. So write an inequality here. All right, so we have side 15 matches side 15. The only other side that matches is this reflexive one in between. So now we have this side angle side possibility with side angle side possibility. And 20 is the small compared to the big 50. So the consequence there is side angle side small and side angle side big simply means that this is smaller than this big. And so the inequality that we get is AB is less than CD. Okay, now let's look at the other one. I'll do givens in blue. So we know 4 is the same as 4, and we know the reflexive is shared. So the only thing that we know then is big side, SSS inequality to small side, says that this side, angle side, or side, side, side compared to this one, means that there's a bigger angle here than there is small angle here. And so our only inequality that we can establish then is PQS, so measure of angle PQS, is big when compared to the measure of angle RQS. Now notice though that we could also compare some angles based on these side lengths of 4 and 8. We could always say that, you know, the angle opposite the 8 in one triangle is bigger than the angle opposite the 4. And so now we can start chaining together not just separate triangles, but then connecting them and saying, look at this, what we know. Okay, so let's go to the next one. Write an inequality to describe the possible values of x. I love these ones. Okay, so these aren't going to be as straightforward as you think. All right, let's look at this. What the heck? We have these 3 are equivalent, so we know all these are 60. Oh, that might be useful, maybe not. Okay, and then we have that 45 there, and we have that. So what does that tell us? Well, let's look. I wrote all the 60s in there because look at what's going to happen. We know 2 sides are congruent and 45. Here we have 2 sides are congruent and 60. That means this is big compared to this small across from 45. So that's exactly the Hinge theorem, right? The forwards, not the converse. And so this tells us that x plus 5 is bigger than 3x minus 7. But what else do we know? We always have the fact that x plus 5 is a side length and 3x minus 7 is a side length. Maybe that won't matter, right? So like minus 5 minus 5, x is bigger than negative 5. Maybe that won't matter, but maybe it will. Plus 7, so 3x is greater than 7. So dividing by 3, x is bigger than 7/3. So maybe that won't matter, maybe it will. But the real inequality they wanted us to use here was subtracting the x from both sides. Remember, I always move it to one side, so I'm dealing with positive x's, so I'm never dividing by a negative. Then you add the 7 to both sides, and you get 12. So dividing, we get x is less than 12. So we actually have all of the possible values is x is bigger than, x is less than 12. Which way should we write this? 1, 2, 3. Yeah, big should be on this side. And then small should be on this side. So x has to be bigger than -5, but it also has to be bigger than 2 1/3 or 7/3. So that means really all we have to put here is the 7/3. Because any number that's bigger than 7/3 is always bigger than -5. Whoa, that was a cool one. Okay, let's try another one. All right, so over here, what do we have? We have a 7 and a 6 match to a 7 and a 6. And then the third side here in one triangle is big, and the third side in the other triangle is small. That means that this angle is small, and this angle is big when compared to one another. So that means the 7x plus 4 is small when compared to 140 degrees. And so we get -4 minus 4. So 7x is less than 136. Did we forget something? Divide by 7, divide by 7. So x is less than, it's a little less than 20. So what is it? It's 19 and 4? 3/7 maybe? Maybe that's right. What's that? 70, 63, and 3. Yeah, I think that's right. So you could either leave it either way. I like it this way too. So x is less than that, but what did we forget? We forgot to always say that it has to be bigger than 0. It's an angle that exists. So that means -4 minus 4, 7x is bigger than -4/7. So, I already skipped to the punchline there. So so now we have x is greater than -4/7. So actually, we weren't done with this inequality down here. That was just the upper limit, but the lower limit is it can go all the way down close to -4/7. So actually, there is a limit both at the top and at the bottom most of the times. Interesting. Okay, so write an inequality relating the given pair, okay? Well, the first one says AB and FD. Well, it literally gives you AB is 9, and it gives you FD is 6. So that was easy. AB is bigger than FD. So I'm just going to circle the bigger one. That one's bigger. Okay, that was a silly question. Now let's go to the next one. It's talking about angle FD or BDC. So this angle when compared with FDB. So FDB, this angle over here. Okay, I'll use different marks. Well, look at this. We have a 6 and a 6, and a 9 and a 9 is congruent to itself. And then it opens to a small here, and it opens to a bigger here. And so that means that these angles then, remember this is our SSS inequality, or a converse of the Hinge theorem, saying if the same two sides, a 6 and a 9, open to a 4 or a 6, the 6 is wider, right? So that simply means that the FDB is the bigger. This angle is bigger. All right, so then let's erase that. Let's go to a different triangle. Or not different triangle, different comparison in the same triangle. So FBA, that's this angle, compares to DBF. So D to B to F, this one. Okay, well, let's look. Oh, again, it's got a 9 and a 9, and it shares a 6 here. It's really common, this reflexive property in the middle. Okay, so now we have a bigger 10 compared with a smaller 6. So then going in, that means this angle's smaller and this angle's bigger. So the FBA is the bigger one there. Okay, so pretty straightforward. Just use the theorem, right? Just apply it, okay? Let's go to the next one. Write an inequality relating the given pairs of angles. So same sort of question, except now, no, I mean, really it is just the same type of question. All right, so AD and DC. So AD, so we want to talk about this side compared to this side. So to do that, we're going to need to talk about some side angle side, okay? Well, if I'm looking at this triangle, whoa, I don't have a side, I don't have an angle, I have a 3 there, that's useful. And compared to this, well, I have a 3, but I don't know this angle, I don't know the side. So maybe take a step back and zoom further, and now look at this. Okay, they share this side and an 8. And then this triangle has an 8 and shares that side. So the 60 is bigger than the 40. So this is bigger and this is smaller. Okay, so AD had to be bigger there, and that was because we zoomed back. Cool, cool. So I'm going to erase that. Okay, and now the next one is OC and OA. So OC and OA. Again, it's like, well, if I look at like this triangle and this triangle, that's not enough. I don't know. But we were given all this information up here. So the 8 is the same as 8. The reflexive in the middle. And so we have big angle 60 opens up to big side. Small angle 40 opens up to small side. So AO is bigger in that one. All right, and the last one here, just clean this up again. AOD. So we got AOD. How does this one compare to AOB? AOB, this one. That's tough. Okay. So what do we have? We have they share a side. We have, oh, no, we can't use that. I was going to say, well, they share a side here, and then we have an 8 and an 8.11, but that's just not enough, right? So instead, what can we do here with flipping it over and maybe looking at their vertical angles? No, not yet. Let's look though at the top. What do you see here at the top? We have this 8 and this 8 which we haven't used yet. So let's erase that and let's erase this really quick. Well, let's just fill in some more stuff that, because I mean we were stumped there, right? We didn't have enough to go forward. But look at this. We have an 8 and an 8 which is an isosceles triangle. We have a 100-degree angle up here, which means we have two base angles that add up to 80. So this was 40 degrees. And this was 40 degrees, right? That's 180 isosceles triangle. Well, we could even go a little further. That means these two sides, because the 40, these two are congruent. We could also just add up a triangle and get that's 80. So this is 100. So that means this is 80. That means this is 100. And that means this is 80. Oh, are you starting to see how maybe we could use some congruent sides here to figure this out? Do you see it yet? How could we compare which one's bigger and which one's smaller here? Well, there was no comparison. It's already done, right? We're not trying to jump to a side or anything. We literally have the angles. So it was just AOD is bigger because we numerically solved for it. So don't be scared of falling back on past information. That was just base angle theorem using isosceles triangles. Whew, cool stuff. Okay, let's do another one. So write an inequality to describe the possible values of x. Well, a couple of things. Like one, it's a side, so this is greater than 0. That's a thing. Okay, and then let's look. Well, we have a 8 and an 8, and they share a side. Okay, and then we have a big angle and a small. So that means 10 is smaller than this. So we get the 3x minus 2. Has to be the big side when compared with a 10. Okay, so this at least we go plus 2 plus 2. 3x is bigger than 2, so divide by 3, x is bigger than 2/3. And then here we go plus 2 plus 2, 3x is bigger than 12, divide by 3, x is bigger than 4. But those are redundant. If I'm bigger than 4, I'm already bigger than 2/3. So what, is there no upper limit? Would this triangle never get ripped apart? Well, let's go back and look at this though. What do we know, right? So like often a thing we don't write down when we get to one of these is because, for example, in this problem, x was a number of degrees. We actually should have included 7x plus 4 is less than 180. Even if it took up 99.9999% of all the degrees, it has to be less than that. So we minus 4, we minus 4. We get 7x has to be less than 176. So x is less than, and that would have been like, I don't know, 20 plus. It was bigger than 20 because 20 times 140 is 140. And so this was already less than 19. So this was already true. So, okay, so it was good. We didn't need to check at that time. We got lucky, okay? We weren't careful. But here, what do we know, right? Whatever this side length is here, well, and there's a limit, right? What can this side length be? Let's call it y. Okay, this is just a cool problem to think about, right? Y has to be between, right? Just using the triangle inequality, right? The biggest it could be is if 18 and 10 were straightened out to almost a line segment. Couldn't be a line segment, then it wouldn't be a triangle. And it has to be bigger than 10 minus 8 is 2. So that side length is somewhere between 18 and 2. Okay? So the biggest this could possibly be, right? The 3x minus 2. Let's do it off to the right. The 3x minus 2. The biggest it could be is the maximum 18 plus the maximum 8. So the biggest it could be was this, and the smallest it could possibly be. It couldn't just be 0, right? It would have to be an 8 and a 2. Oh no, the smallest it could be is if it was 8 and an 8. Yeah, it could just be really close to 0. Okay, so if that was, right, if this was a length of 8, we could swing it to where this was infinitely close to 0. Okay, so we did that one already. So this was the upper limit. And if you didn't follow that, oh, that's so cool. I'll explain it one more time. Is less than 26, we add the 2, we get 3x is less than 28. So x is less than 28 thirds, or about 9 and a third, or not about, that's exactly 9 and a third. So altogether, we get x has to be bigger than 4, but less than or equal to 9 and a third. Oh, snap. That was cool. Again, that was like, I'm throwing extra curveballs at you that probably most teachers would just gloss over, but it's just cool. So what I did there is I said, well, we don't know the other side length here. And so seemingly there could be no limit to this, because this side length could just keep getting longer and longer and longer, and great, any number works. However, that side length's restricted in this. Right, in that triangle inequality theorem tells us any two sides have to add up to be bigger, right? I always thought about it as a river and two bridges need to cross the river. So two sides need to be bigger than the third. And so that triangle inequality theorem tells us that this is the limit, right? That side length here, y, oof, that's so scribbly and messy. That y there can only be between 2 and 18. Can't be 2, can't be 18, because then it would be a straight line. But it has to be somewhere in that range. And so then I thought, well, then what is the limit of this side related to the 8 and the y? Oh, that's my alarm, because I got to zoom in just a minute here. Okay. So then what that means is the longest it could possibly be is if there was an 8 and 18 stretched end to end. And so that was the maximum I put here. It couldn't be that long, but it could be infinitely close to that long. What a cool problem. Okay, let's do another problem, and then I'm going to pause the video and jump to Zoom, and I'll come back. Okay, in this one, write an inequality. So we're going to have 100 inequalities. This is where you put it all together. This is the culmination of first semester, right? Okay, let's see what we know. Well, on the left, these are all the same. So what kind of triangle is that? Yeah, equilateral. Yeah, what does that mean? Equiangular. Okay, so we got 60, 60, 60. Maybe that'll help. And then over here, oh, a 58. And look at this, we got isosceles. So those two are the same as these two. And so what does that mean? That means slightly bigger to slightly smaller. That means this is smaller than the other, okay? All right, so let's first rewrite the bigger x plus 2 is to the smaller 2x minus 8. Well, then what else do we know also? Okay, we also know x plus 2 has to be bigger than 0. And we also know 2x minus 8 has to be bigger than 0. Is there anything else we know? I mean, there's so many things in this picture. It seems like there should be more, but I don't see anything off the top of my head. I mean, really, there's only two side lengths, so knowing how they compare is pretty much everything you can know about them. And then they're both bigger than 0. It doesn't seem like there's an upper limit. I mean, we could go, just to double check, we could go x plus 2 plus x plus 2 has to be bigger than 2x minus 8. It's just a triangle inequality. Triangle inequality here is redundant because you know it's an equilateral triangle. And then over here, we'd also say x plus 2 plus 2x minus 8 is greater than x plus 2. And then the only other one is the same thing. 2x minus 8 plus x plus 2 is greater than x plus 2. And you see that once we subtract the x plus 2 from both sides, we just end up getting 2x minus 8 is greater than 0, which we already have on the right. So both of these end up being redundant. Let's check this one. 2x plus 4 has to be bigger than 2x minus 8. Oh, that's always true. We subtract 2x and we get 4 is bigger than negative 8. Turns out this one was always true no matter what. So triangle inequality didn't give us useful information, but let's go ahead and solve for this. So minus 2, x is bigger than negative 8, or negative 2. Okay, add 8, 2x is bigger than 8. Dividing, we get x is bigger than 4. Oh, okay. And then over here we get subtracting x from both sides. Oh, here's our upper limit. I see it. And then we add 8, and we add 8, and we get x is less than 10. And so putting all three of those together, we get that x must be between 10 and 4. Very cool. Okay. Shoot, do we have extra time? I'll do one more. No, I'm going to pause it. I'll come right back from Zoom. Okay, I'm back. Wow, time traveling is crazy. I don't even know when you're watching this. What year is it right now? We're still in crazy 2020. COVID quarantine. Whew. Okay, I'm just dating myself. Here we go. So this one, we're going to try and use that same theorem, right? So we're going to the fact that sides are bigger, so that hopefully we're going to find a side with an angle in between where one is big and one is small. Okay, so let's look at what we got. Well, we have PQ is the same as QS, okay? So I'm going to mark that right in the middle, but it's a little sloppy because you can't tell which side that's applying to. And then, oh look, and QR is the same as itself. And what we want to get is that PR is bigger than SR. So look at that. We're talking about the two angles then that we're talking about is this whole angle and this little angle. Well, we could use the angle addition postulate to just say those add up and then the definition of inequality. So let's establish this, okay? So first, we know that PQ is congruent to SQ. That was just a given, okay? We also know that QR is equal or is congruent to QR. Okay, so those are our two congruent sides. Now we need to talk about those angles in between, almost a given. That's a reflexive property of congruence. Okay, so we got those two. Now we need to somehow deal with the angles in between. Because if, and I'm just going to kind of pencil this, I'll just write it in, but we don't really have it yet. If we could get that the measure of angle PQR is bigger than the measure of angle SQR, right? Like if we could get this for whatever reason, well then that means we have two congruent sides and a bigger angle in between, and two congruent sides and a smaller angle in between. So then that would mean the big angle opening up to PR makes a bigger side than the small angle opening up to SR, right? Which is what we want to get in the end. And that would be the Hinge theorem or the SAS triangle inequality, right? So whichever way you want to call that. So the question is, how do we get to this angle thing? Well, I think we're just going to use the angle addition postulate because we know, I'm just going to delete our little scratch notes here. We know that the measure of angle PQT plus the measure of angle TQR adds up to the entire angle. What do we want? SQR, PQ. Oh, I'm going to rename this from TQR to SQR just so it matches, right? And that's adding up to a total of angle PQR. So that's the angle addition postulate. Just to remind you of what the angle addition postulate says, is it just says you can add up two angles, right? So here, just to erase my markings in the picture, I'm saying that this angle plus this angle adds up to total, right? That's it. Just 10 degrees plus 20 degrees makes a big angle of 30 degrees. Okay, that's it. But now we could use the very definition of inequality, right? Since angle measures are always positive numbers that exist, bigger than 0, then I know SQR plus positive stuff to get to PQR means that this is bigger, right? If you add positive numbers to get to the bigger thing, then that's the very definition of inequality, right? That's I won't go repeat myself, just remind you of it. But if you have a number and you add a positive, non-zero positive number to it to get a bigger number, then by the very definition of inequality, that means that the bigger number is bigger than the smaller number. That's it, okay? And once we have that, then we have the Hinge theorem proving that. So that was really just, other than the given, we only added 1, 2, 3, 4 little steps there. Cool. All right, so let's do another one. This one may be a little trickier, okay? So let's see. Here, it looks like we've already got two congruent sides, and we've already got two congruent sides. So it looks like we're pretty set up here. We want to prove that this side is bigger than this side. Well, it looks like we're exactly set up. How can we do that? So remember to do that. So I'm just going to write out the givens. To do that, we need the angle in between to have some relationship. Well, how do we relate those angles in between? Can you think about it while I write this out? Okay, well, let's look at the picture. What relates this angle to this angle? I'll give you a hint. Right? So here we know that A plus B is equal to C. But again, just like we mentioned above, if you start with an angle A and add positive to it to get to C, that means C is bigger than A. And similarly, C is bigger than B. That's our very exterior, originally this was our exterior angle theorem. But then a consequence of it, kind of corollary, is the exterior angle inequality, which says that the exterior angle is bigger than either of those two remote interior angles. And so we could establish that down here. So we could say, okay, so this was given. And then the angle between them, so let's just make some room here. The exterior angle, measure of angle SUT, is bigger than the remote interior angle, measure of angle USV. That's the exterior angle inequality. And then you put those together, that's side angle side. You have the angle between is bigger, two congruent sides. That means the bigger angle opens up to a bigger side. So that means ST has to be bigger than UV. That's the SAS triangle inequality theorem, or it's the Hinge theorem. Whichever one you want to call it, whichever one your book uses or your teacher uses. Okay, so here's two more. I'm just going to kind of rush through these. They're really the same as what's been going on. So here we have triangle ABC. So we have a triangle. And then you know that AB is the same as CD. Okay? So again, by reflexive property, this is congruent to itself. So we have two congruent sides opening up to the same two congruent sides here. So we need some way to talk about this angle, or the sides they open up to, AD and this. Well, we want to prove the relationship between the sides, BC and AD. So we need a relationship between the angles, and we just did it, right? So here we'll just say, given AB is congruent to CD, given, or not given, but BD is congruent to BD by reflexive property. So here's reflex, here's given, and then we have the angle. So angle 1 bigger than angle 2. I know we need measure of. That's the exterior angle inequality. And then we say, whoops, inequality. And then we put all three of those together, and the Hinge theorem says that the smaller angle 2 opens up to a smaller side, so BC is bigger than AD. So it's really the exact same as the proof we just did, and so here's the Hinge theorem. All right, so I just kind of rushed through that. What about PQ is the same as RS? So PQ is the same as RS, got it. Reflexive property, these are the same. We want to get that 3 is big. No, sorry, 3 is small. Let's just write over that. Small. And 1 is big. So that means we need to somehow get that this is a big side and this is a small side. And we're given QR is smaller than PS. Oh my gosh, this is crazy. It's so straightforward. So we literally just establish, we go, well, we were given PQ is congruent to RS. That was just a given. And then we say, well, and also QS is the same as itself. So we've got the two congruent sides. Oh, not given. That was reflexive property. Reflexive prop congruence. Okay, so now we've got this set of sides and this set of sides. And then we have the third thing, which we were given, which is just the relationship between the sides. So that is that QR is less than PS. And so now that we have three sides, right, one being different, but the other two being the same, that's the very SSS inequality that tells us that the bigger side opens up to the bigger, or is opening up the bigger angle, and the smaller side's opening up the smaller angle. So that tells us the measure of angle 1 is bigger than, let's write it in the same order as they want, is less than the measure of angle 1. And that's the SSS triangle inequality. So I just rushed through both of those because they're really the same as the ones we've done. All right, hope you enjoyed the video. Oh, and I just at the end here, I threw in the proofs of the two theorems. Now, I'll walk through it a little, but really it's beyond the scope of this class. So you have to use an indirect proof for the last one. But for this one, what you do is anytime you have a bigger angle and you're dealing with an inequality, basically what you do is you just make the same angle. So you say, okay, so we got this other angle. So we go, okay, well, let's just make this same angle over here. And then we could use some angle addition to say, okay, well, the whole thing is less than a smaller. So that's how we make the angle. And then we just place a point. And now the point is useful because you say, where am I going to place this point? Well, again, I'm going to do it at an equal length. So I'm going to place it so that ZF is the same as BC. So in other words, I'm making this same triangle, the same value over here. So this is just in the same point as B in space, right? Same length, same angle, SAS, they're the same, right? That's what I'm doing at that point. Can I point a line segment based on an angle? Yeah. Now point a ray. So now I have this ray that goes on forever. And then could I measure some distance and plop Z down? Of course I can. I can just measure any distance and put Z any distance along that line segment. Okay, so that's what we did. So essentially we just created B on that other triangle. Well, one case is, what if Z lies on the line? Okay, well that's easy. Then the triangles are congruent because I literally made them congruent. I drew them the same. And so if they're the same, then we have that. And then we just go, oh, segment addition postulate. If Z is on DE, that means piece plus piece equals whole. And so that means the whole thing, by definition of inequality, is bigger than the piece, right? Because if you have DE and it's equal to two things added together, then ZD plus something, positive side length, means that ZD originally was smaller. We had to add something to get to it. And then you just substitute the equal value in. And so we got what we wanted. D is bigger than AB. So that was the easy case. What if it's already on the line segment there? Okay, but what if it's lying in space like that? And this is where the proof gets kind of crazy. So I didn't want to do it because I honestly would have stumbled a lot, rearranged things a lot. So I took my time. I went off basically the book's proof too. But if it's not, then this is what you do. You just say, okay, so here's this point. Well, then you just say, okay, I've already got this, which is the same as this triangle over here. Then what you do is you just draw the angle bisector here. That's it, okay? Angle bisector of that. Angle bisector exists. Got it, all right? And then we just named the point V here is where that angle bisector hits DE. All right, and then, again, I don't want to walk you through this. This is boring, but basically we just use a bunch of tricks of chains of logic to say triangle inequality theorem. So any two sides are bigger than the third. We use that. And then we use the segment addition, and then we use congruent triangles to add all this up. So here's our segment addition, and then we have two sets of congruent triangles, and we just put all that together and we get the inequality we wanted. ED is bigger than AB. It's pretty clever, and I'll post the notes and you can absolutely walk through it. But I do like the indirect proof. I just wanted to mention it, okay? So remember, an indirect proof is simply showing that everything else is impossible. And so you're left with the thing you wanted to prove is the only possibility. And so here's what we have, okay? We start with this given, and then to do the indirect proof here, what we're going to do is we're going to assume the opposite of this is true, okay? So the opposite of greater than is less than or equal to, right? So it really has two separate cases. Either it's equal or it's less than. Okay, and so I prove it two separate ones. Well, if the length is, so if this opposite of this that we assumed is that they're equal, well then that means the angle here is equal to the angle here. So the triangles are congruent by SAS. That's nothing special, that's it. And then look at what happens though. We were given that RT is bigger than UV, but if the triangles are congruent, then these are the exact same. So we can't have them to be the same length and RT be bigger than UV. That's impossible. So in the case where the angles are the same, it's impossible. So can't be. Angles can't be the same. Okay, we know that. Well, what if angle S is less than angle W? Well, same thing. We just go, oh, okay. Well, then we have that angle S is less. This is more. And so literally that's just the Hinge theorem. That just says, okay, well then this side is less, and this side is more. And so, what does that mean? RT is supposed to be, in the given, this one's supposed to be more. So that's impossible. You can't have it be less and have it be more. That's impossible. So this case is also impossible. So the only possibility left, because any two numbers on the number line are either less than, equal, or greater, and so then this must be true. So that's the goal of kind of an indirect proof. So cool little, I rushed through those, but you can always read through the notes. All right, guys, I hope you enjoyed the video.